Today we will be working with trigonometric identities. This corresponds to sections 6.1 and 6.2 in your text. Details about our objectives are here, but in short, we will be looking at identities, old ones and some new, and then we will also be using these to prove other identities, along with using some of the algebra skills you brought with you to Math 172 for verifying additional identities. So that the important identities that we have covered related to today's lesson is at your fingertips. They are available on this slide. In addition to the fundamental identity or Pythagorean identity that we have already covered, sine square x plus cosine square x equal 1, there are two more identities that completes this set of identities. They are 1 plus the cotangent squared of the angle equals the cosecant squared of the angle, and the tangent square of the angle plus 1 equals the secant square of the angle. And to conclude the identities we need for sections 6.1 and 6.2, we also have our odd and even identities for trig. Odd and even identities were actually covered in the previous course, Math 171, but now we have these identities for trig. All of these identities you should learn so that you'll be ready to use them easily when you're taking your tests. Well, at this point, we will be focusing on verifying additional identities. So just looking at a guideline for doing so. Depending on what you're trying to prove is equal, that determines which of these procedures you may use. Of course, some of the problems will require more than one of these procedures. First, start with what appears to be the more difficult side of the given identity. Try to transform this side so that it eventually matches identically to the other side. Don't hesitate to start over and work with the other side of the identity if you're having trouble. Try using one of the following techniques to begin, and then use others if necessary to continue the verification process. Technique 1. Look for ways to use known identities, such as the reciprocal identities, definition identities, and odd-even properties. If the identity includes a squared trigonometric expression, try using a variation of the Pythagorean identity. Of course, all of these identities here in bold were just shared with you. Method 2. Try rewriting each trig expression in terms of sine and cosine. Method 3. Factor out a GCF and use factoring techniques, such as factoring the difference of two squares or the sum or difference of two cubes. Method or technique 4. If a single term appears in the denominator of a quotient, so just one term in the denominator of a quotient, try separating that quotient into two or more quotients. And you see that symbolized here. Technique 5. If there are two or more fractional expressions, try combining the expressions using a common denominator. And of course, that is symbolized here. Technique 6. If the numerator or denominator of one or more quotients contain an expression of the form a plus b, try multiplying the numerator and denominator by its conjugate. And finally, technique 7, to convert one rational expression into another, multiply the numerator and denominator of the first by either the numerator or the denominator of the desired expression. Now looking at some examples. An example of substituting known identities to verify a new identity. We are given the tangent of x times the cotangent of x equals 1. Well, we need to verify or prove this by making the one side of the equation identical to the other side. Of course, using our reciprocal identities, we know that the cotangent of an angle is defined as 1 over the tangent of an angle. Things that are equal, we can replace one with the other. So making that substitution, we're able to cross cancel because that is allowed with multiplication, leaving us with a left-hand side equal to 1. The right-hand side was 1. So now this identity has been verified. In other words, this is not just something someone stuck an equal sign in between. The left-hand side of this equation is actually equal to the right-hand side. In other words, this is a true statement. Continuing with an example of the technique changing to sines and cosines to verify an identity. This example is the tangent of x over the secant of x is equal to the sine of x. Well, we're changing to sine and cosine, so that means the tangent of x must be replaced with its definition that involves sine and cosine. We know the tangent of x is equal to the sine of x over the cosine of x, making that change or substitution. The secant is also defined as 1 over the cosine of x, so making that change. We have a complex fraction. The middle major fraction bar means to divide. We're dividing by a fraction, so we use that procedure, invert and multiply. Once again, we're able to cross cancel because we have like terms, so cross canceling out the cosine of x, we are left with the sine of x equal to the sine of x. Yes, the left-hand side is equal to the right-hand side. So this identity is true. It has been verified. Looking at an example of another technique for verifying an identity, factoring to verify the identity. The identity given is sine x minus cosine square x times the sine of x equals the sine cube of x. So of course, starting with the more difficult side, usual approach, we have a GCF, a common factor of sine x, so we can factor it out. After doing so, we're left with a Pythagorean identity, 1 minus cosine square x, which we know is equal to sine square x. So we're able to make that substitution. Finally, multiplying on the left-hand side of the equation, we end up with sine of x times the sine square of x, which will give us the sine cube of x on the left-hand side. That is identical to the right-hand side of the equation. So this identity is correct. It is true. We have verified it. Now we have an example that is just a little bit more complex, but still requires substituting known identities to verify. We're given sine square negative theta plus cosine square negative theta equals 1. So to start off with, I'm just moving the exponents to their usual location, which is behind the term, and that is the usual location outside of trig, so that this problem looks a little bit more typical to all math covered up until this point. At this particular time, we can apply the odd and even properties, which allow this negative sign to be put in front. And of course, Here, our negative sign with cosine just goes away. Now squaring, if we square the understood -1, it is inside the parenthesis with an exponent of 2 on the outside, we get a positive understood 1, leaving us with sine squared theta plus cosine squared theta on the left-hand side. That is a Pythagorean identity equal to 1. So once again, we have made the left-hand side of the equation equal to the right-hand side, so another verified identity. Sometimes, if you're given a single quotient, a quotient with one fraction bar, single quotient, you have to divide it into its meaning, into more than one fraction, in order to verify the identity. That is the case with this example. So, placing both terms in the numerator over the understood denominator of sine x. After doing so, we know anything divided by itself equals 1. So sine x divided by sine x gives us 1. At this point, it gets fun. We know that a fraction bar means to divide. So this is the cosecant of x divided by the sine of x. However, with fractions, we know we can divide once again by inverting the sine of x. Understood denominator 1, we flip it, we invert it, we get 1 over sine x. We invert and multiply to take care of division. When we do that, we can remember that 1 over sine x is an identity, it's a reciprocal identity for the cosecant of x, so we can make that substitution. So if we substitute the cosecant of x here, we're left with the cosecant of x times the cosecant of x, which is the cosecant square of x, bringing down the -1. And we have another Pythagorean identity, cosecant square x minus 1 is equal to cotangent square x, and this identity has been verified. Next, sharing with you an example of multiplying by the conjugate to verify an identity. So here's the identity we need to verify. In our denominator, we have a difference, 1 minus sine x. Of course, the conjugate is always identical, but with the opposite sign. With this problem, we're actually multiplying by the conjugate of the numerator. So we have 1 plus sine x. We are multiplying it by 1 minus sine x. Of course, you see the multiplication symbolized in the denominator by writing things side by side. In the numerator, we're multiplying two binomials, so remember to distribute both terms. You may have also been accustomed to doing this by using the for method. So first gives us 1, then we have minus sine x plus sine x, that combines to 0, and then finally sine x times sine x giving us sine square x, and it's minus because we have unlike signs, excuse me. We have another Pythagorean identity in our numerator, so we can replace it. 1 minus sine square x equals cosine square x. Copying the denominator, 1 of the cosine x will cancel out, it will reduce, leaving us with cosine x over 1 minus sine x. So this time we made the right-hand side identical to the left-hand side. Here's the final example so that you will have one of each type. There are more examples in section 6.2 in your textbook, and these types of problems just require practice. You will receive practice through your homework exercise. Here you're given two separate fractions. You have to get a common denominator and write it as one fraction. The denominators on the left-hand side are cotangent x, cosecant x, so we put those together for our common denominator. Remember, whatever you multiply your denominator by to get the common denominator, your numerator must be multiplied by the same amount. After doing that, the procedure is just a repeat of things that we have performed throughout this PowerPoint video.